Going to question number 2, a block of mass M is released from rest at position x equals 0. I won't do all the reading here. You can kind of see it from the picture that at x equals 0, that's where the block is at rest. It starts to accelerate down the ramp and then starts hitting the spring and compressing it. It says at x equals 8d, that's when the block makes contact. And then I have this part boxed in red already. It comes to rest at x equals 12d. All right, so let's go ahead and jump ahead and we're going to draw some energy bar charts. So it says the shaded bars should start at the dashed line that represents zero energy, represent any energy that is equal to 0 with a distinct line on the 0 energy line, and the relative heights of each shaded bar should reflect the magnitude of the respected energy consistent with the scale used in figure 4. Okay, this is an important part. When something has 0, you want to make sure you have a distinct line to show that it's 0. All right, they give us a huge hint in our first one. We have kinetic energy right over here of 7 E naught. We have a UG of 2 E naught, and then we have a spring potential energy of 3 E naught. Okay, so 7 plus 2 plus 3 is going to give us that 12 E naught total. So we know that our total energy is going to be 12, which means we need to have 12 bars of energy in our first and second graph because it says everything is within the system. It says block, spring, earth system. So it says right over here, block, spring, earth system. So that's basically everything. And then there are no there's no work done on anything done on the system or by the system. So all of our 12 E naughts of energy are going to remain in different forms, but there's going to be 12 total. All right, so let's go to our x equals 0 position. So that's where it's at its highest position. There's no velocity, no kinetic energy. The spring is not compressed, so all 12 go to our UG. And we have the distinct line right here for our K, and we have a distinct line for our US. Now, going to 6D, that is half the diagonal distance down the ramp, and it is also half the vertical distance down the ramp as well. So what I thought about in my head is we have an unknown theta, but say, for example, that theta was 30. If you take the sine of 30 times the length that it moves down the ramp, that would give you the vertical distance or the height the block is at. So sine theta times 12 would be a height of 6. And then sine theta times 6d would give you 3. So it does drop to half the height. So I did that little double check in my head. All right. So with that being said, since it's dropped half of its height, you could see here that my UG goes up to 6, and then the rest is pretty easy from there because it hasn't touched the spring yet. So I definitely have a distinct line at 0 for my US, my spring potential energy, and then the kinetic energy would definitely have to go up to 6 as well so that we have a total of that 12 units of energy as we did for our third graph and our first graph. All right, let's go ahead and move on to the next part. It says that figure 5 shows block x equals 0. The block is released from rest, and the block at x equal 12 released from rest, and the block at x equals 12d when the block momentarily comes to rest against the compressed spring. So it is all gravitational potential energy, which we know as mg delta y or mgh, and then it becomes all spring potential energy, which is all 1/2 kx squared. All right, so sliding up here, this is where I put my work. So for gravitational potential energy, it's mg times delta y, or the height. So like I said before, it's sine theta times basically your hypotenuse of 12d, which is the diagonal length of the ramp, and that equals 1/2 kx squared. Okay, now I put 4d because remember it started to contact the spring at 8d, and then it came to rest at 12d. So the amount of compression it got was a distance of 4d. So when you go ahead and square that, that becomes, whoops, that becomes 16d squared when everything gets all squared. All right, so if you take the 1/2 and multiply both sides by 2, that brings a 2 right next to the mg. And then you divide both sides by 16d squared. You can see my 16d squared dropped right underneath in the denominator. One of the d's drops out. And then your numbers are 2 and 12 on the top, which is 24, and has 16 on the bottom. That fraction simplifies down to 3/2. And then you have 3 mg sine theta divided by 2d, and that is equal to k, your spring constant. For C, it says figure 6 shows a graph of the energy of the system as a function of the position of the block from x equals 8d to x equals 12d. So the whole time that the spring is getting pushed in and you have some spring potential energy. All right, so it says sketch and label a line or curve that represents the total mechanical energy for the block spring earth system as a function of the position of the block from 8d to x equals 12d. So I put a nice straight line here in red. I mean, it's not that straight, but it's meant to be straight, showing that 12 E naught total, just like my bar graph. So that is my E total. So I made sure I sketched it and labeled it. Secondly, it says sketch and label a line or curve that represents the gravitational potential energy. Whoops, kind of cross that out. Gravitational potential energy for the block spring Earth system as a function of the position of the block from x equals 8d to x equals 12d. Now, each time the spring gets compressed 1 unit of it's saying it's 1d, I guess. So from 8d to 9d to 10d, it is decreasing its height by 1 unit as well. So it is a linear decreasing curve. So it's going to start from 4e. So I know that because it started with the full 12 of energy, and then if it slid down to the 8d position, okay, then it would drop 8 units of energy. So this is when it has no movement at the very beginning of the ramp, and then when it slid down 8 units of energy, it lost 8 E naughts basically, and then it's going to start from 4 E naughts, and then once it reaches its base position, the gravitational potential energy reaches 0. So I have a straight line that goes from 4 to 3 2, 1, and then 0. Okay, and I wrote straight because I didn't do a good job of drawing a straight green line. For part D, it says indicate whether the speed v9d of the block at x equals 90 is greater than, less than, or equal to the speed v8d of the block at x equals 8d. Okay, so my first inclination is to say that at the lower position, v9d is greater than v8d. Now I want to make sure I find some evidence that supports that. So it says justify how your response is consistent with energy lines or curves you drew in figure 6 in part C. All right, so let's slide back here. Now, if we have 4 units of gravitational potential energy at that point, to fill up our full 12 bars of energy at that point, our kinetic energy would be 8 E naught. Now, when it goes to position 90, it goes lower on the ramp. So naturally, we would think if it loses gravitational potential energy, it's going to gain kinetic, and it's a total no-brainer that it's going faster at position 9D. But at that point, we have more spring potential that's introduced. So we have 4 units of gravitational potential energy, and then kinetic filled up the additional 8. Over here, we have 3 units of UG, and then we have, it looks like slightly less than 1 unit of US, the spring potential energy. Okay, you can see the little cross-sectional area over there. So because I can tell it's a hair less than 1, if something slightly less than 1 is added to 3, then we have a number slightly less than 4. Therefore, this line over here is going to be about 8 E naught, but it's going to be a little bit greater. All right, so sliding down over here, Justify response, conservation of energy, 12 E knots total. I would have been a little bit more thorough writing sentences, but I just did an abbreviated version here. At position 8D, my UG is 4 E knots. Therefore, my first K, called it K1, equals 8 E naught. At 9D, my UG equals 3 E naughts plus a spring potential energy that is less than 1, which was very slightly less than 1. Therefore, my total of those two is slightly less than 4 E naught. That means that my K2 is slightly greater than 8 E naught. And if K2 is greater than K1, then my V2 has to be greater than V1. As I said, if I was doing the real justification, I would definitely have written that out in a few sentences.